And now we're going to get the second derivative of the function x squared plus y squared is equal to 25 using implicit differentiation. So let's go ahead and start with our first derivative. So notice that I am writing out all my notation so I can easily find, or I can easily use my rule in implicit differentiation for x squared, y squared, and the constant 25. And for the first term, my derivative is simply 2x because I am deriving or differentiating in terms of x. But for the second term, which is y squared, my differentiation will be 2y dy dx because I am differentiating for the function y in terms of x. And we know that the constant is simply 0 because of the derivative rule for a constant. Now we're going to find dy dx by isolating the dy dx in our function. And this is now our first derivative. And sometimes we can call this as y prime as well. So different notations for the derivative of a function will help us in organizing our work. So now that we are done with the first derivative, now let's go ahead and find the second derivative of this function. So the second derivative in terms of x of the function negative x over y would be found using the quotient rule. And as we know, the quotient rule, I use low d high as my mnemonic device, minus high d low all over low squared, so that I would know or I can remember the formula for the quotient rule really easily. So my low is simply my function at the bottom and my high is the function at the top. So low is copy. So we have y derivative of high minus high derivative of low. Notice that I am not looking at my signs right here because I'm just going to set it aside so I can simply focus on my function x all over y for my quotient rule. And then I'm going to use my negative sign later on so that I will avoid confusion in my work. So let's go ahead and simplify our derivative. So we have y, derivative of x is simply 1, minus the derivative of y, which is going to be 1 times dy dx all over low, which is y squared. And by simplifying this, we know that our function dy dx is simply negative x over y, and we're going to substitute this in our derivative function to find our second derivative. So our function will now look like this. So this is now our derivative function, which we can, or the second derivative, which we can simplify into y plus x squared all over y squared, which is our second derivative. Now, the challenge in the next stage of my work is how to simplify the complex fraction into a single fraction, and to do this we're going to be using algebra. So we can still simplify this second derivative by doing this method. So let's go ahead and simplify our second derivative. So our second derivative was y plus x squared all over y divided by y squared. And by using algebra, what we can do is we can multiply this complex fraction with the common denominator, which is y. So by doing so, we can eliminate the y in the denominator in our numerator. So by multiplying this whole thing by y, which is simply changing the look of our rational function. So by doing so, we will multiply y to the first term, to the second term, and to the first term right here, and to our denominator. And our fraction will now become y times y is y squared. Y times x squared all over y. This cancels out. So you'll only have x squared right here. And this one is y cubed. So now we have gotten rid of the complex fraction in our derivative, which is now our simplified version of our second derivative, which can also be rewritten as d squared y all over dx squared. So these are some of the notations that we use in our derivative function. So that's our first example. Now let's go ahead and work on another function, and this time with a given point. So now we're going to find the second derivative of square root of x plus square root of y equal to 3 at a given point, which is 1, 4. So let's start with our first derivative. And before I move on to my derivative rules, I'm going to change my function into x raised to 1/2 plus y raised to 1/2 equal to 3. So I can use the power rule for my derivative function in a little while. So the derivative of x squared in x raised to 1/2 plus y to the 1/2. So the derivative of x with respect to x is simply 1/2 x to the negative 1/2, and the derivative of y in terms of x will look something like this: negative dy dx, which is equal to 0. Now, we know that dy dx can also be changed into y prime as our notation, and I'm going to use this later on so I can easily evaluate my first derivative. So by isolating my dy dx, I will subtract negative 1/2. Subtract 1/2 x to the negative 1/2 on this side of the equation. So I'll end up with now notice that I changed my dy dx into y prime because I can easily set up my equation to isolate my dy dx by doing this method. So by changing my exponential function into its radical form, I'll have y prime all over 2 square root of y equal to negative 1 all over 2 square root of x. And by doing so, I'll be able to isolate y prime using ratio and proportion. So I can just cross multiply this. So I can just multiply 2 square root of y on both sides. So I can get rid of this. So y prime is by itself, and it's going to be negative 2 square root of y all over 2 square root of x. So it's a lot easier to see how to isolate y prime when your functions are in radical form. So by simplifying this, y prime, we can evaluate y prime to the given point 1, 4, which means we can substitute the value of y and x and give us square root of 4 all over square root of 1, which is equal to -2. So our y prime evaluated at a given point 1, 4 is simply -2. So we're now finished with the first half. Now let's go ahead and find the second derivative of this function. So for the second derivative, we know that we're trying to find d squared y all over dx squared of negative square root of y all over square root of x. So in this case, I will use the quotient rule once again. And quotient rule is simply low d high minus high d low all over low squared. Alright, so changing this to negative y to the 1/2 all over x to the 1/2 will make it a lot easier to differentiate. So low d dx of high minus high and d dx of low all over x to the 1/2 squared. So in this case, finding the derivative of our function will be simply x to the 1/2 times, this one is going to be 1/2 y to the negative 1/2 times dy dx minus y to the 1/2 and 1/2 x to the negative 1/2 all over x raised to the 1/2 square is simply x. So now that we have our derivative, now let's change it back to its square root format. So we'll have square root of x multiplied by 1 over 2 square root of y dy dx minus square root of y and 1 over 2 square root of x. So this is our second group, this is our first group all over x. So now that we have our derivative set up, we know that we are finding the second derivative evaluated from 1 and 4. So what we're going to be doing is substituting the value of y and x by 4 and 1, and of course we have a dy dx right here, and we know that our dy dx is -2. So by substitution and simplifying our rational expression, we'll be able to find the second derivative at this particular given point. So let's go ahead and do our algebra work. So once again, we are working on y double prime of 1, 4 of square root of x times 1 all over 2 square root of y multiplied by dy dx subtracted to square root of y times 1 over 2 square root of x all over x. Now that we have set it up, what we're going to be doing is to know that our x is 1 y is 4, and y prime, or the dy dx, is equal to negative 2. And we're plugging it into our equation right here. So now we're going to have square root of x, which is 1, multiplied by 1 over 2 square root of 4, multiplied by the derivative, which is negative 2, minus square root of 4 multiplied by 1 over 2 square root of 1. And don't forget that this is all negative because our derivative function is negative all over x. And we're going to use this again later on because from our derivative function we know that the first derivative was a negative fraction. So simplifying it, we'll have 1 times 1 all over 2 times 2 minus 2 times 1/2. And by simplifying this all over 1, by cancellation, we can cancel this, 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 and this, and we are left with negative 1/2 minus 1 all over 1, and we know that this is negative. And by simplifying the numerator, negative 1/2 minus 1 is simply negative 1/2 minus 2 all over 2, which gives us negative 3 all over 2. But since we know that our function is supposed to be negative, the second derivative of the function at 0.14 is simply 3 all over 2. And this is how we found the second derivative of our second example. Now for our last example, and for our third example, let's take the second derivative of the function 2x cubed minus 3y squared equal to 8. And by isolating that dy dx, we'll end up with so this is now our first derivative, and to find the second derivative we're going to be using the quotient rule. So y double prime of x squared all over y will be low times the derivative of high minus high times the derivative of low all over low squared, which is y times 2x minus x squared times dy dx all over y squared. And dy dx, as we know, is x squared all over y, so we will replace x squared all over y by our first derivative, and we'll end up with 2xy minus x squared multiplied by the dy dx, which is divided by y squared. And by simplifying this, we'll have 2xy minus x to the fourth all over y divided by y squared. And we know that we want to get rid of the complex fraction, and to do that all we have to do is to multiply the numerator by y and the denominator by y. And by doing so, we'll be able to get rid of the y in, or the complex fraction in your numerator. So we'll have 2x y squared minus x to the fourth all over y cubed. And this is now our second derivative, which can also be written as this. And that is how we find the second derivative of higher order, second derivative using implicit differentiation of higher order derivatives.